Welcome back to the May 2025 IB Chemistry TZ2 SL Paper 2 walkthrough. We are continuing on with question 1, parts B and C, so just the second page of the exam. And so this is talking about, essentially now we're going into weak acids, strong acids, sorry, not bases, weak and strong. Okay, there we go. And so this part B starts off with some background info is that HCN acts as a weak acid in aqueous solution. This makes sense because, as we know, anything that is not our big 5 strong acids are going to be weak acids. Our big 5 are going to be nitric acid, sulfuric acid, HCl, HBr, and HI. Okay, anything else, weak. So HCN is not one of those, so it's going to be weak. Okay, and it says to write an equation to show this behavior. So to do this, we need to think about what in the heck a weak acid even means. Okay, and so a weak acid means that you're going to have partial ionization, okay, rather than a complete ionization, okay? And so whenever you have partial, that means essentially an incomplete type of reaction. So the only way that we can represent that is an equilibrium, okay? And that is the really big difference in the equations for strong and weak acids, is strong acids are always a single arrow, weak acids are represented in equilibrium. And so the equation they're looking for is literally just the ionization with an equilibrium arrow, okay? And so ionization always looks like HA. I always write state symbols just for funsies, for plus and A minus, where you're just forming the dissociating into the proton and conjugate base. Okay. And so for a strong acid, it would look like this with a single arrow. For a weak acid, it will then be that way. And so then we're just going to plug this in for HCN specifically. So HA would be our HCN, our acid. Okay. So HCN, always write state symbols just for funsies. Okay. And then it's going to dissociate into the proton. And if you don't remember what the heck the conjugate base is, it's literally just what is left after you take away the H, the CN. It has to be minus because it's the ion. Ooh. So that's the answer to that. Okay. It's just the equilibrium. Okay. You also could have done a reaction with water. That was also an option. But I feel like the equilibrium is just a bit more straightforward and easier to comprehend. For part 2, it says to outline 2 ways in which that you can determine if a solution, a 0.1 concentration of HCN, was that or HCl. It's the same concentration for both of them. And so this is a classic question they ask all of the freaking time. And it is essentially just how do you distinguish experimentally a strong acid versus a weak acid of the same concentration? And there's always, every year, a couple options for this. And so the biggest one is that mostly things are all good as long as they're right, except for one thing, and the biggest misconception, okay? And so we're going to clear up this misconception before we even get into the question. The right answer, okay? It's the wrong answer, the misconception that they want you to put, because everybody thinks it, not everybody, but a good amount of students still fall for this, is this misconception that because this partial ionization, that if you do a reaction with a base or any reaction with this acid, okay, is that a weak acid, if you put it through the same reaction compared to a strong acid, the yield of the product would be lower because you have essentially a lower amount of starting materials, okay? And so even though this is an equilibrium compared to a initial kind of reaction, the stoichiometry is still the same as long as it is the same number of ionized protons. Okay, so since this is HCN and HCl, they're both monoprotic acids. Okay, if this were monoprotic versus diprotic, that would be a different story. So you couldn't do this problem with like sulfuric acid instead of HCl. And so your stoichiometry is still the same. So your maximum amount of products is also going to be the same. The stoichiometry does not change. And that's a major misconception. As students will say, oh, if you react it with like a carbonate, then there would be less CO2 produced for HCN compared to HCl. And once again, that is not true. You would have the same amount of products being produced. The one thing that would change is you're so close, the speed. It would be the speed, okay? And so that's the first method one that we're going to put, because that's the one that I always think of, is we're going to say react with same base, same concentration, And so whenever it says to outline the two ways, is you also want to put both like the method as well as the expected result. Okay. Because, and since this is 2 marks, that means for both method 1 and method 2, both the method and the result, even though it doesn't really explicitly ask for it, you still need to say it, are going to be, it's going to be an and mark, if that makes sense. Like it's not, if you just put react with same base, same concentration out the expected result, the way to distinguish it, then you would not get the mark. It's an and mark. Okay. So same concentration, and then you would say that HCN, that's terrible handwriting. HCN would react slower. There we go. So that's how that would go. Method 2, I always immediately think of electrical conductivity, because electrical conductivity is based on the presence of mobile charged particles. Okay. And so because we have little less ionization, we're going to have less mobile charged particles, and therefore they are going to be less conductive compared to like HCO, which has more mobile charged particles because of its complete ionization. Okay. So I'm just going to say electrical conductivity. And then we'll just say that HCN would be less than HCl. HCl would have more. Okay, so that is going to be the answer to that question. There were lots of different options here. I'll put the mark scheme here. You'll notice that some of them are oriented more towards the HL syllabus. If you said as an SL student, I mean, you didn't need to know that. But anyways, like the part about kind of like the equivalence point, all that is that would be there. But you could also do that. You could also do things like pH. If you do the color stuff of the like universal indicator or like the test strips, you would have to exactly say the color that would be expected. So you'd say like, oh, more red versus kind of more orange/yellow. You would have to say that and get specific for that mark. Okay, and so there were lots of options here. For part three would be to determine the pH of the 0.1 moles per decimeters cubed solution of HCN if the concentration of H plus is 7 times 10 to the negative 6. This is a very straightforward calculation. If you forget it, it's in your data booklet in that section 1. It is that the pH is the negative log of H plus. So that is there if you forget. And so this is just going to be the negative log of that 7 times 10 to the negative fifth. Or is it 6? It's 6. I'm having a stroke. 6. There we go. So we're going to do that in our calculator. So negative log 7 times 10 to the negative 6. And that's going to get us 5.15 for that question. Okay. And then this last part C for this question 1 is going to be with hydrogen cyanide reacting with hydrogen in this equilibrium equation. And so the first part is to write the expression for the equilibrium constant. And so the expression for the equilibrium constant is always going to be the concentration of the products over the concentration of the reactants. And each concentration is raised as an exponent to its stoichiometric coefficient. Okay, so first we're just going to write the concentrations before handling the exponents. We're going to go K is equal to the concentration of CH3 and H2 in our numerator divided by the concentration of HCN and H2 gas. Okay, then we're going to put in our exponents. So there's none other than for H2. It has a 2 there, so it's going to be raised to the second in our equilibrium expression. It is worth noting, once again, we're not solving for a value here. This is just an expression. So that is why we're just writing the variables, if you will, the concentrations. Okay. Then this next part for part 2 is to determine the oxidation states that indicate that carbon is reduced in this reaction. So we need to solve for its initial oxidation state and its final oxidation state. And so in this, we have HCN. And so we can find the oxidation numbers of hydrogen and the nitrogen and then solve for carbon. And so to do that, we can look at our periodic table, which pretty much corresponds with the oxidation state rules. So hydrogen is going to be +1. I'll actually write these here. So we have like +1, plus 2, plus 3, plus 4 slash minus 4. Carbon can go either way. That's why we solve for it, rather than assuming nitrogen minus 3, minus 2, minus 1. Okay, and so that is where we kind of are. And so we can say that HCN overall, it has to equal 0 because it's a neutral molecule. Okay, so we have plus 1 plus carbon, and then nitrogen is minus 3. It's going to be equal to 0. So I'm really bad at math in my head. Listen, so that means that carbon is going to be equal to plus 2. There we go. So we're going to say our initial oxidation state is plus 2. Our final oxidation state, we're going to do the same thing just with here, with the product. Okay, so we have carbon, and then each hydrogen is plus 1. We have 3, 4, 5 of those. So carbon plus 5 minus 3 is going to be equal to 0. So that means that it then is going to be equal to minus 2 for our oxidation state here. So it goes from plus 2 to minus 2, which is indeed a decrease in oxidation state. And that concludes question 1 for that paper 2 of SL.